Welcome to The World, the Universe and Us, the weekly news podcast from New Scientist. I'm Rowan Hooper.
And I'm Penny Sarche. Yes, this is the show where we discuss the must-know science stories of the week. If you're new to the show, welcome. It's great to have you with us. We have some corking stories to get stuck into this week. We have a report on a landmark new study into the nature of consciousness, and check this out. That is a dolphin responding to the sound of its name being called. For the first time, scientists have analysed the whistles made by wild dolphins and derived their meanings. So that's coming out.
Corking, Penny.
Do you not use the word corking?
In the 1950s.
It's a mainstay for me.
Oh, okay. We're going to start, Penny, though, with a small new finding that the sky is, in fact, not blue.
What? It's gloriously blue today.
Yeah, well, this story feels as big as if the sky suddenly was not blue.
Okay.
Because light, in fact, is not what it seems. That's what this story is about. New research has just been published that could upset this classic experiment from physics, the double-slit experiment.
Right, so that is a super famous experiment, an icon of physics.
It is.
Yeah.
I thought if I tried to think of classic physics experiments, I might think of Galileo dropping a feather and a stone off a building, Newton shining light through a prism.
Yeah.
And the double-slit experiment. That's the finding that if you shine light through two slits, it interacts in such a way as to show that light is both a particle and a wave.
Yeah, so we call this wave-particle duality. There's this dual nature of light.
Well, that's what we thought, and that's what this week's story is all about. So there's a new interpretation of the double-slit experiment that suggests we got it wrong.
Okay.
And that means that we got the whole nature of light wrong, which is quite a big deal if you think about it, which is why I said, the sky's crashed in. Chelsea White is here to talk about this. Chelsea, better take us through the double-slit experiment first.
Sure thing. First of all, I think, a lot of us learn that light is a wave before we think of it as being made of particles called photons. Is that your experience? That's how I thought of it.
That's definitely how I remember learning it. Is that not historically how we thought about light? We thought it was a wave and then we learned it can be a particle.
I mean, we've kind of gone back and forth for a long, long time. Because it's really hard to pin down what light even is. So in the 17th century, Isaac Newton did propose that light was made of particles that he called corpuscles, which I think is a really great word.
Kind of gross.
Yeah,
sounds like something from your body.
Yeah.
But then, we get this experiment later on that shows that light is a wave. And I think it sort of makes sense that we would hang on to that idea a little bit more because in our everyday life, you think you see maybe sun shining and you think of it as like a wave or a ray. And I personally don't think of it as a bunch of particles hitting me.
No, definitely when you're out in the sun.
Right. So this experiment, this was first done in 1801. And it's a pretty simple setup.
That's a long time, longer than I thought, Chelsea. They were doing this physics experiment.
They were. And then the funny thing is you get this experiment, you have some findings, and then the interpretation of those findings keep changing as we have things like Einstein come along and this new study this week. So if you're setting up a double-slit experiment, as you might want to do, you have a light source like a light bulb, and then there's a couple of screens between the bulb and a detector screen. And the first screen basically just funnels the light towards the second. But the second one is where things get a little weird. Mm-hmm. So that screen has two slits, which might be obvious based on the name. And you might expect if you shine enough light passing through them that you would just get two strips of light on the detector screen where those slits were.
Right.
But we don't see that. And that's the funny thing. So instead, you get this really wide spread of alternating light and dark strips. And the way we made sense of that was that this theory of light being not just a particle, but a wave too. And the way that those waves sort of fan out after they leave the slit and then interact with each other and cancel each other out, that's where we get that distinct double slit pattern.
Okay, so that's the classic interpretation of this experiment. What's changing now?
Yeah, because I thought the classic double-slit experiment, it's classic. We all know about it. Even biologists know about it.
Yeah.
It's been done many times, many different things.
Well supported.
So, many different versions of it. So what's gone wrong?
Well, what's wrong, they're saying, is just the interpretation. So these researchers started out and they said, what if we don't assume that light is a wave? Could we assume that light is only particles and then still have the math work out so that you can produce that same distinct double slit pattern? And surprisingly, to me at least, you can. But then you have to ask the question, what's going on in those dark parts of the pattern. Because if it's not waves of light hitting each other and canceling out, and that's why there's no light there, what is it? So these researchers suggest that there are photons, particles of light, touching the entire detector screen from left to right. And the places that are dark are just where there's a collection of dark photons, which I think you can think a little bit of like dark matter.
Dark photons.
Dark photons.
Oh my God.
It is bit mind-blowing, that.
Yeah.
So I asked one of the physicists if he could explain it. This is Celso Villa-Boas of the Federal University of São Carlos in Brazil.
There are two main types of light particle states. Ones that interact with matter, which we call bright states, and the others that don't interact with matter at all. Those are the dark states. So what we are essentially saying is that in the dark spots of a double-slit experiment, where we don't detect light, there are still photons there, but they are in dark states, meaning that they are not interacting with matter. In other words, the photon is spread out through all the space, but in some regions it interacts with matter, and in others it does not.
So dark photons can't interact with matter, so we don't see them, but they are still there. It is a bit confusing, this. I mean, didn't we already think that photons were quantum particles, Chelsea?
Yeah, you're right. We did. But I think the reason that this feels huge to me is that for a long time, we've taken the results of the double-slit experiment, which, as you said, has been done for hundreds of years, over and over. And we've taken it as a sign of something really definitive about the nature of light. This new interpretation doesn't contradict what we know about the particle side of that wave-particle duality that you mentioned earlier. And so some of it just has to do with, how we approximate reality so that we can understand it. But it is really hard for me to shake the things that we've been taught for decades. While I was editing this piece, I kept asking our reporter, Carmela Padovich-Callahan, all of these questions, and they kept coming back to me saying, yeah, but your question is still based on the idea that light is a wave. So you kind of have to change your whole way of thinking about it.
Yeah, because we talk about wavelengths of light, sunny day, I'm putting on sun cream, and thinking about UV, it's high energy. How do we reconceive color and how we think of as light if there aren't waves?
Yeah, so I guess we just understand that color, which changes based on what we have usually called the wavelength of light, is just actually due to a photon's energy. So its vibrational frequency will determine what color we see.
Are you telling us is the sky blue or not, Chelsea? Come on.
I mean, what is blue is sort of a philosophical question, but based on physics, I think the answer is yes and no, kind of, because it's about how we perceive it, right?
Yeah, I mean, it is philosophical, isn't it? I mean, it's the color of the sky is what our eyes sense and what our brain interprets. So it's not really that color. What is it really?
Yeah. But, based on this new interpretation of light, if you're hit with a bunch of low energy photons, you'd see red, and higher energy ones look like us to blue. So I guess you can still have your blue sky.
Oh, thanks.
So this is fascinating to think about. But is this just flying a kite? What do the other physicists out there think of this idea?
Well, the authors of the study said that within their team, once they'd come to their conclusions, quote, all hell broke loose.
I'm imagining smashing up the lab and running rampage.
Like that meme.
Yeah, exactly. And one of the researchers even said that he's already changed how he's teaching about the double-slit experiment in his classes. But responses from outside the team ranged a bit. No one told us that this looked outright incorrect, of course, but many said it was really controversial, and some questioned, sort of why we would even need this new framework for understanding the double-slit at all. And so they were asking, so for instance, if this radical reinterpretation of a 200-year-old experiment can tell us anything new about quantum physics, or if it changes any other findings in experiments outside of this one with light. And the answer is we just don't know yet, but it could.
Well, it could. It's very exciting. I spoke with Gerhard Remper at the Max Planck Institute of Quantum Optics. He's the guy who said all hell broke loose that we just heard. Let's listen to him because he puts it very well. And also he's German, and it feels right to have this physics explanation in a German accent.
In a nutshell, we have found a new view on classical interference of waves in terms of entangled quantum states of particles. We have achieved this in a fully quantum mechanical description. First, the detector used to observe the interference pattern is treated as an essential part of the system. And second, the interference is described as resulting from entanglement. The entangled states are found to be bright or dark, depending on whether they couple to the detector or not. A characteristic feature of the dark state is that it contains photons, but that these are unobservable for the detector. It means that photons are present at the nodes of an interference pattern. A highly counterintuitive conclusion, I would say. In conclusion, we have learned that our quantum picture provides a more general description of interference than Maxwell's equation. And that's actually quite interesting.
I think that's suddenly become my favorite piece of understatement.
Yeah.
This result makes more sense than James Clerk Maxwell.
Only him.
Only like one of the most famous and important physicists of all time. And that's quite interesting.
Quite interesting. Next up, we have the results of a 7-year study into the nature of consciousness. Yes. And it turns out there's quite a bum fight going on.
A bun fight. There isn't. A bun fight is a tussle between supporters of rival theories, for anyone who doesn't know that idiom. And the
It's a corker.
It is a bun fight and a corker. The two theories in question that the bun fight is happening between are both attempting to explain how consciousness arises, so how the brain creates the conscious experience.
Yeah, only one of the biggest questions in existence. Yeah. And there was this famous bet, wasn't there, about consciousness, whether or not we could explain it from a neuronal point of view. So that's how the actual cells in our brain produce
there
it.
was. We'll come to that. And one of the people who made the bet is Christoph Koch.
Mm-hmm.
He's from the Allen Institute of Brain Science in Seattle, and he worked with Francis Crick for many years before Crick died on explaining consciousness. Christoph is a supporter and a proponent of something called integrated information theory, which claims that consciousness can be defined on this mathematical spectrum. And that's one side. And the rival theory of consciousness is called global neuronal workspace theory.
Okay, so my understanding of integrated information theory is quite out there, isn't it? It suggests consciousness arises from any system whose components exchange information in a way that can be sort of defined mathematically.
Yeah, that's right. Any system.
Yeah.
So it could be a table or a rock or a bird or a human. So I asked Christoph Koch to expand on this for us.
So according to the integrated information theory of consciousness in principle can be completely dissociated from behavior, including things like intelligent behavior. Intelligence and consciousness are really two very different things. IIT predicts that a consciousness occurs in any mechanism like the brain where there is a maximum of cause-effect power, which has to do with the way neurons are wired to each other. And if you look at the wiring in the back of the cortex, compared to the wiring in the prefrontal cortex, the wiring is quite different. In the back, it's more topographic, reflecting visual and auditory and somatosensory spaces. In the front, it's more random access. And therefore, IIT predicts that the maximum of cause-effect power, the physical substrate, the neuronal footprints of consciousness are in the back, which is the prediction that was borne out by experiment 1.
And they measure that amount of connection with a value called phi, PHI, that is the Greek letter phi. So the theory says the more integrated information, the higher phi, and the more conscious the system is. And so to talk a bit more about this, I asked Anil Seth. He's a neuroscientist at the University of Sussex, big friend of new scientists, and author of a great book on consciousness called Being You. And I asked Anil to explain.
What it does is it takes this broad definition of consciousness and then it says, okay, what are the properties of conscious experiences in general? And two of these properties, oversimplifying horribly, are integration. Every conscious experience is one experience. It's all of a piece. And information. Every conscious experience is different from every other conscious experience. And so if every conscious experience has this combination of integration and information, well, then you can start to do some maths, and in the end, you come up with a way of measuring the degree to which any system has both integration and information. And that is phi.
So a rock, say, would have a low integration and therefore only be lowly conscious. So if there's this kind of a gradient, where would something like a newborn baby be?
Well, so that's where things get interesting. People have said, well, what about not even a baby, a fetus?
Yeah.
Or someone in a coma.
Yeah, minimally conscious states and this kind of thing.
So that's why it's become really controversial. We'll get into that a bit more in a minute.
Okay, so that's one of the explanations for consciousness, or proposed explanations.
The other one is a global neuronal workspace theory.
They need to work on these names, don't they? It's quite hard to hold in your consciousness.
If anyone's got better names, let us know.
Yeah.
Global workspace theory suggests that information competes for attention in different parts of the brain, cortical and thalamic brain regions. And if one signal outcompetes another, it gets broadcast across the brain and that becomes conscious.
Oh, I quite like that.
Yeah. Well, that transmission happens at the beginning and end of an experience. And so in this theory, it's tied to the prefrontal cortex at the front of the brain.
Okay, so these are quite different theories. How then, if we're sort of putting them head to head or in a bun fight, how could people test between them?
So they got 256 people had their brains scanned while they looked at objects such as faces and letters and things and identified different aspects of them. And then the scientists examined very carefully which parts of the brain were processing those images and how long they were active for, how long they were synchronized for. And this took 7 years.
7 years.
Crunched all the data and inconclusive.
Oh, after all that. That's science, I suppose.
Yeah, well, we still learned a lot, and there's support for some aspects of both theories. And Christoph Koch emphasized that when I spoke to him. Well, he would do because he supports one of the theories, integrated information theory. Here he is again. He talks about corvids here. That's obviously crows, magpies, those birds, because the work suggests that consciousness comes from the back of the brain. And as we know that birds don't have a prefrontal cortex, but they might have consciousness. So that might explain why we do think that those sorts of animals are conscious. And he also talked about what we've learned from people with lesions in different parts of the brain that knock out brain function in different areas.
This implies that there is this brain basis for consciousness, which may be different than the brain basis for intelligent behavior, including reasoning, thinking, social judgment. We know this from lesion studies over the last 150 years in clinical neurology, that if you have large strokes in the back, typically they go hand in hand with loss of entire classes of conscious experience, like you don't see color anymore, you don't see faces anymore, etc. While lesions in the front typically don't affect consciousness at all, but they might impair your moral judgment or your social judgment, where you keep on saying inappropriate things. This also has implications for evolutionary considerations, since we like the prefrontal cortex because in humans it's maximally expanded compared to, let's say, even the great apes or monkeys or all other mammals, which again gives primacy to us humans. But there are lots of other animals, such as corvids, such as squids and octopus, that have cortical-like structure that are highly integrated, that have the same topographic connectivity. And so per IIT, that would suggest they could be highly conscious, although they may not appear as intelligent as we are.
That's amazing because, in neuroscience, we hear a lot about the prefrontal cortex because we're obsessed with our own brains. And I don't think I'd really thought about, intelligence and consciousness aren't actually exactly the same thing and they could be coming from different bits of the brain.
Yeah, highly conscious.
Yeah.
But less intelligent.
But not quite as intelligent.
Fascinating idea, isn't it? Here's Anil Seth again.
What I found most interesting was that some predictions from both theories didn't hold up. For integrated information theory, you didn't see the kind of sustained activity in the back of the brain, in the posterior hot zone, that the theory predicted. And for global workspace theory, you didn't see these offset responses in the front of the brain that the theory predicted. So that puts some pressure on the theoreticians and the experimentalists to figure out, why not?
So why has this bun fight broken out now then?
Well, so the issue is really over this IIT, integrated information theory. I mean, you joked about a rock having a low level of consciousness, but as we sort of hinted at, if you start saying, a fetus has, it can cause a lot of problems about how you deal with those conscious entities. So even according to IIT, a primitive computer may have a kind of level of consciousness.
Isn't that part of the appeal, though, that there's kind of a spectrum rather than you're either conscious or you're not? Like animal studies do suggest, insects might be a bit conscious.
Yeah, that is part of the appeal for sure.
Yeah.
But it remains to be seen which one comes out on top. I suspect it won't be resolved because it won't be able to answer the big question after all of consciousness.
And what about that big bet then?
Well, so that's the big bet was between Christoph Koch and philosopher David Chalmers, and this was in 1998. Koch bet that we would have a neural understanding of consciousness in 25 years' time, which obviously we didn't get to. So in 2023, Koch conceded the bet. He presented Chalmers with his prize, which was a case of fine wine. And I asked him about this as well. It's quite nice. So he is here.
So David Chalmers and I famously lost my bet against David Chalmers regarding will the field have converged. This was now 2023 on a universal accepted neural footprint of consciousness. It is not. So I gave him 6 bottles of wonderful 1988 Madeira wine. Yes, and we opened one of them and drank them.
Handy for Christmas.
Nice.
That's lovely. All right, on to marine mammal language for our next story.
As we do.
Yeah, of course. So we're getting much better at decoding and understanding the meaning of whale song, aren't we? That's something you've reported on in the past.
Of whale song, yeah. So especially sperm whales, humpback whales, there's all these very complex clicks and stuff, and we're decoding those. So,
really exciting. But this new work is on dolphins. Now, what I do know about dolphins is that they have names, don't they? They have these sort of distinct whistles that relate to each dolphin, which is quite cute.
Signature whistles, they're called.
Okay.
So the dolphin might say something, and then at the end of the sentence, they add this signature whistle. So it would be like me finishing this sentence and saying, Rowan.
Quite useful in communicating long distances.
It is.
And stuff. Yeah,
it
okay,
is.
Cool. So you're saying that they're actually saying something and then showing out their name. Is that taking it too far?
Yeah. Okay. So, that's what the story's about.
Okay.
We do know that there's these signature whistles, and then there's another class of noise they make called non-signature whistles.
Okay.
So listen to this first. So that's a dolphin in Florida. All of these recordings that we're here, they're from free-ranging dolphins in water in Sarasota in Florida, part of the Sarasota Dolphin Research Program.
Okay, so that whistle, what did it mean?
That was a non-signature whistle, and it was an alarm call. And the researchers think that because when you play it back to dolphins, it causes an avoidance behaviour. So this is the difference with this study, is they've been able to apply the noise and see a behaviour, and that's how we're able to decode what it actually means. And now here's another one. So that's another non-signature whistle. And researchers think that's a query. So the dolphins make that noise when they hear something unfamiliar. And now listen to this one. So that's 2 males together. And what they've done there is the researchers have played the name of one of them to the 2 males. And then they've responded with a query.
Like, what are you doing?
Like you would do.
Yeah. What was that?
Yeah.
So it's like if I went, Rowan.
What? Yeah.
Okay.
What is it? Yeah, exactly.
Right.
You query it when you hear your name.
Yeah. Okay, so this is cool. And it's the first time that we've been able to assign meaning to this kind of whistle, other than the sort of name signature ones. And you said that they were able to do this by sort of pairing behaviour that was observed with the whistles that were given.
Right.
And that's been going on for decades. It's involved 170 wild dolphins.
Yeah, this study has.
So we know a vast amount about these dolphins.
Yeah, we know a lot about their generations, some because they live a long time, so we can relate them all. There's a huge amount that biologists have learned about this population.
One thing I've always been curious about, who names a dolphin? Do you come up with your own signature, or does your mum give it to you?
Well, so I wondered that as well. I asked Layla Sayer. She's the lead researcher on this new work, and she said that they know signature whistles are learned, but we don't know if the dolphin makes up their own name or if they're given the name or they choose them. the name based on some other thing. So we know
they're learned, so they're not innate. They're not sort of
we
born
know they're
just
learned.
knowing what they think
Correct.
their name is. Right,
Yeah.
okay, but
Yeah.
we don't know who's coming up
But
with
we
it.
know that some develop signature whistles that are a bit like their mum's name. Some are like their siblings or other community members, but we don't know quite how they choose them.
Intriguing.
Yeah.
Okay, so we don't think this is quite language, is it? It's a bit too simple for that.
Yeah.
But this is the first evidence in dolphins for a wider repertoire of, I guess, sort of shared signals with a kind of context-specific meaning.
Yeah. So Layla calls it, says that dolphins are good candidates for language-like communication. And partly they're good candidates because they're lifelong learners. They're very vocal. And here she is.
We know that they produce name-like sounds called signature whistles, and they also copy those whistles, the whistles of other dolphins, as a way of initiating contact with them. So that suggests that these sounds might be used referentially, the way names represent other individuals to us. We also know that they use something similar to what we call motherese or baby talk, where we speak with a sort of higher inflection when we're communicating with infants or young children. And we found that dolphins do something similar. So there's a lot of evolutionary parallels between their communication system and ours. And now we have started to find this wide repertoire of shared non-signature whistles that we're trying to understand how they function and whether they might also potentially have reference. And just one last thing, I guess, about AI. I do think that AI would be very useful to help in automating categorization of whistle types, and that's something that we're currently trying to utilize AI for, but I don't think that AI is a panacea for decoding animal communication. I think the only way the meaning of sounds can be discerned is by knowing the context of their production, which means linking them with observations of what the animals are doing. AI can detect patterns and things, but we have no idea if they mean anything to the animals unless we have context.
Wow, that's amazing. They talk in baby talk and dolphin.
Motherese.
Love it.
That's all for this week. You've been listening to The World, the Universe and Us.
Same great show, new name.
Do go ahead, subscribe, get in touch. Also, we'd love to hear from you.
And thanks to all our guests, and thanks to you for listening.
And see you next week.
Bye.